We'll start by looking at finding the center of mass of a rod of uniform density. So a rod is a long, thin object. So we're going to look at its linear density, or its mass per unit length. So for the entire rod, that would be the total mass of the rod divided by the length of the rod. But because it's uniform density, I can take any size piece of the rod and its mass to length ratio will be the same. So m over L is my linear density, and that's going to be the same as some incremental mass dm over the incremental length dx. So if I take that and solve it for dm, I get m over L times dx. When I look at our equation for center of mass, the coordinate for the center of mass is 1 over the total mass times the integral of x dm. So I want to integrate with respect to coordinate x and not mass m as indicated in the integral. So I need to relate the mass dm of each piece of the rod to its length dx. So that is done right here for me. So I'm going to take this dm and replace it with m over L dx. And now I can integrate with respect to x. So, and my limits, I'm going to show you two ways where I place the rod along the x-axis. Doesn't really matter. If I place its center at the origin, then I'm integrating from the left side to the right side, which would be negative L over 2 to positive L over 2. Or if I offset it so that its center is not at the origin, here I've chosen to put the origin at 1/4 of the way along the length of the rod. So my limits of integration would be from negative L over 4 to positive 3L over 4. And you can pause the video and follow the math. You can see that I still get my center of mass of the rod to be right in the center. Here my integration came out to be 0, which is an x-coordinate of 0, which is right in the center of the rod. And when I use these limits of integration, I get L over 4, which is L over 4 is right there, which is still the center of the rod. Now let's look at finding the center of mass of a rod of non-uniform density. So I'm going to still use the same idea that the incremental mass per the incremental length is the linear density, but now it's no longer a constant. Now in this equation, or in this example, they tell me the linear density of a rod varies with the length according to the equation 2x plus 3. So if the length of the rod is L, find the location of the center of mass of the rod. So gamma is a Greek letter that is often used to represent density. So that's what I've done here. Gamma is 2x plus 3. I again start with my same equation for finding the center of mass of a rod. And now my incremental mass over my incremental length is gamma. So now I'm going to cross multiply here. Gamma times dx is equal to dm. Okay? But gamma is 2x plus 3. So now in my equation for dm, I'm going to use 2x plus 3 dx. And 1 over m is not just a number, it's the sum of all the incremental pieces of mass. So that's the integral of dm is my total mass of the rod. And dm, I see over here, is 2x plus 3 dx. So x dm, there he is, x dm is 2x plus 3 dx, and integral of dm is integral of 2x plus 3 dx. And so now you can follow along the integration. I'm separating out the terms and integrating them separately. And then when I plug in my limits of integration, you can follow it along here. I come up with my final answer for the location of the center of mass of the non-uniform density rod right here, 4L squared plus 9L over 6 times quantity L plus 3.